Early software that ran on the very first microcomputers typically assumed a teletype was used as the operator's console. And that's because the paper tape reader and punch on the teletype served as mass storage for the system to allow loading and saving programs. And you've probably seen me demonstrate this in a number of my other videos. Now, as a modern day hobbyist, if you wanted to run this early software, you could of course use a teletype. And there's no better way to bring back memories, and it makes for a great demonstration. But it certainly doesn't take long until the slow speed, the difficulty typing, and of course all the noise just gets to be a little overwhelming. So if you're going to continue to use this old software to do any sort of serious work, it doesn't take long until you break down and start using a terminal emulator on a PC. Of course, the console screen serves as a nice silent 9600 baud or even faster terminal, and the fact that you can send and receive files through that very same serial port duplicates the functionality of the paper tape reader and punch. Of course, it doesn't feel very authentic, which is one reason I always wished you could easily take a vintage terminal and a paper tape reader punch like you see here and combine these two to make essentially a glass teletype that was interchangeable with the original teletype when it came to running this early software. Now you may look at this terminal and this reader and say, well, those aren't very vintage. And no, they're not as old as the computers I just showed you, but both of these devices are now over 40 years old as well, so time just really keeps ticking away. The obvious problem with trying to use these two devices is that they are on two separate serial ports in this case, which of course a teletype, all the devices are on the same single serial port. So the question is, how do you go about combining these? And you may have seen me try using an A/B switch in other videos like this one you see here. And I can sort of make this work. So for example, you might have it set here for A to use the terminal, and you could be doing something and then you need to input from a paper tape, at which point you'd switch it to B, start the reader on the paper tape, let it come in, switch it back to A, and continue using the terminal. And for reads, that works for the most part. If you have a computer like the Southwest Technical that automatically starts and stops your reader, you're not going to get that automatic function. Likewise, any messages that come out while you're loading the tape or immediately after, before you had time to switch this back, you're going to miss out on those messages. So relatively minor, and in the end you could still typically read the tapes, but those are some inconveniences. Now when it comes to punching a tape though, we got a bigger problem. So you're using the terminal, you're on switch position A here, now it's time to punch something, so you do a P command or whatever the punch command is, and by the time you reach up here and switch it to B, you've already missed a bunch of data, especially if we're at a higher baud rate. So punching became problematic when trying to use one of these A/B switches, which is why I decided to come out with this board right here. Let me show you this if I can get a good view of it. I made this little Y adapter board that combines a port from the terminal, a port from the punch, and puts it into a port that's coming to and from the computer. It has a couple of diodes on here that connect from the reader and the other one from the terminal, and that'll wires them together into a single signal that goes into the computer. Likewise, a single transmit signal coming out of the computer goes to both of these ports. And at that point, it looks just like a teletype. And if you were to run this at 110 or even 300 baud, it would work exactly like the original teletype using all the original instructions in the manual. You wouldn't have to change anything. And we have a nice, fully functional glass teletype at that point, just like I wanted. But I certainly don't want to run at 110 baud or even 300. I want to run at 9600 baud. And at 9600 baud, that's a standard rate for the terminal, no problem. Even that reader punch I just showed you, 9600 baud is a very standard communication rate. However, the punch can't begin to keep up at 9600 baud. The throughput, it cannot keep up. Now it's a fast punch. It's, for example, this one's 75 characters per second. But at 9600 baud, theoretically, that's almost 1,000 characters a second. So to be able to handle this, there is handshaking employed by readers and punches like you see. This particular one uses the same handshake lines that you typically find in RS-232. That's the CTS and RTS lines, just wired straight through over to the host computer through that board. And that way it can throttle the punch, and if needed, the host could throttle the reader. Now on the punch, you're pretty much guaranteed to have that capability. The punch will assert RTS when it's ready to accept data, and it will deassert RTS whenever it needs the host to stop sending. Now, with standard straight-through wiring, RTS from the terminal device, in this case the reader, ends up attached to the CTS pin on the UART inside the computer. And what's handy about that is on these older UARTs, the CTS pin directly throttles the transmitter. It's not just a status bit that software has to look at and decide what to do. It directly inhibits assertion of the transmit data ready flag. So your software is already in there polling that, waiting to see when it can send another character. And since it's inhibited, it doesn't know the difference. It just keeps waiting until it says it's time for another character. So that requires no software updates whatsoever. The handshaking just works. So that's a really valuable feature and works great. Now the other direction, having the host throttle the reader. These readers, for example, here can do 400, 500 characters per second. In general, is not needed. And we'll see that in some demos, but we do have a case where the host does need to throttle the reader, and we're going to demonstrate that in one of the later demos. Let's go ahead and get those demos started now. For the first demo, I'm going to use this Southwest Technical 6800 computer. Over here we've got our Glass Teletype, which is this terminal and paper tape reader punch ready to go. In the back of the Southwest computer, I've got the Y adapter board we made. Here's the single cable that runs up to the computer, and then I got a cable for the terminal and a cable over to the reader punch. Now in the end, I don't really like the form factor of this board I made. It's kind of a big rigid block that doesn't lend itself very well to cable routing. Ironically, had I made this back in 1980, of course, I wouldn't have used a circuit board. It wasn't easy for an individual to do. I probably would have just bought 3 connectors and wired those together with a couple of 1-foot wires, easily squeezing those diodes and resistor into the DB9 hood that goes into the computer, and it would have been a better Y cable than that solid block. So newer isn't always better, but it works, so we'll go ahead and just use it here for this demo. All right, I've got the computer on. That $ you see is the prompt from the ROM monitor in this computer. Now obviously the Southwest Technical did not have the big front panel that the Altair and the IMSAI had. Instead it used a monitor called MICBug, or a later version was called SWTPC. And of course it could provide front panel type functions like memory examine, memory change, jump to an address and run. But a ROM monitor could do a lot more than just a front panel. One of the most important features is you could load and save programs to and from memory through your paper tape. And that was a big advantage, in my opinion, of the Southwest, is right out of the box, you could do more with it and more quickly than you could with an Altair or an IMSAI. Another neat thing is these load and punch commands that were part of the monitor automatically controlled the reader, turning it on and off as needed, and the punch, turning it on and off as needed, if you had a version of the teletype that supported those features. What's cool is these modern new readers that came out in 1980 and on also supported those. So when SWTPC wants to turn the reader on and off for a teletype, it's going to work on this one too. So let's go ahead and get this going and show you how it works. So over here on the right, this is 4K Micro Basic for the Southwest Technical computer. And it's a little big for the dispenser on this, so I'm going to hold this up on this screwdriver as my dispenser. All I have to do is hit L, and this will just take off on its own. What did I do? I typed something extra in there. Let me try this again. L. Where are we? There we go. It loads in less than 20 seconds, which is really nice because on the teletype, this takes about 12.5 minutes. So that's a huge improvement. All right, done already. All right, so at this point I can jump to that program up at Micro Basic, up at 100. And that prompt you see is the prompt from Micro Basic. Oops. Let's just do 2 plus 2. One more time. All right, I'm going to take a quick video cut and pick this paper tape off the floor so I don't step on it. All right, that's up off the floor. Let's go in here and write a little quick program. Let's see, I'll just do my usual. All right, let's get a few more lines just so we have some more to save. All right, so there's a program. You've been hard at work, now you want to save it. How would you save this program? Well, this little 4K BASIC has no ability to load and save programs on its own. So instead, you just go back to the monitor. Now we're back in SWTPC, and all you have to do to save this program is hit P for punch. I'll hit P. And there it goes. All right, now the way the punch command works on this 6800 is it doesn't write out the final S9 record until you do the E or N command. That's so you could save disjoint areas of memory. But I'm all done here, so I'm just going to hit E, and that finishes up. All right, and I will just eject the rest of this tape. All right, and so now here we have that program saved as, this is an S record file is the way it saves it. All right, so now you're ready to read that in. All you do is you stick it in the reader. Let's go ahead and go back to BASIC. All right, I'm gonna do a scratch. And so now memory is empty. This is like you just started up for the day. Now you've booted BASIC and you want to load a program. How would you do that? You go to the monitor, type L to load, reads it in, you just type G to go back to BASIC, which the G function is set up to jump through whatever address is stored in A048, and the monitor command automatically sets that up for us. Now the other question you might have, obviously we got our program in here and it works again. When I punched that program, I just went to Mon and I hit P. How did it know what to save? Well, the addresses to use are defined by SWTPC, and it wants the start address at A002 and 3, and then at A004 and 5, it wants the end address. And this already has a value of 0D55 through 0DA7 in it. And that's because that monitor command, when you type it, automatically fills in the start and end address of the punch range for you. So that's why all we had to do was go in there and hit P. All right, so that does it for the Southwest Technical. This works really well with this machine. It integrates automatic start-stop, the punch and the load commands all work. This BASIC obviously is designed to work with the monitor and those punch and load commands. So everything about this is just like using a teletype. Didn't have to change a thing. It's just a lot faster and a lot quieter. So now let's go ahead and take a look and see how it might work with the Altair. Unlike the Southwest Technical 6800 computer that we just looked at, the original Altair 8800 didn't come with any sort of ROM monitor built in. Instead, you use the front panel switches to enter a short program, a bootstrap loader, to give the computer enough smarts to then load a paper tape from the Teletype's tape reader. And that would be like 4K BASIC, for example. Now, entering that bootstrap loader and watching that tape load on the Teletype and then finally seeing the memory size prompt print on your Teletype is basically a rite of passage for any modern day hobbyist trying to resurrect an 8800. And as exciting as that is, though, it doesn't take long until you just really don't want to enter that bootstrap loader every time you want to use BASIC. And this was true back in the day as well. So MITS very quickly came out with an EEPROM board for the 8800 and a ROM called the MBL or Multi-Boot Loader ROM. And that ROM allowed you to load any of their paper tape software programs without having to enter a bootstrap loader. And that's how we're going to go ahead and do this today. So we'll go ahead and turn on the computer, give it a hard reset. The MBL prom is at FE100, so we'll examine that address. That sets the program counter. Now we have to tell the bootstrap loader, the multi-boot loader, what port to use for loading tape through. That's down on these lower four switches. A value of 0 or 1 says to use the console port as a 88.2 SIO. That's what we have in here. The upper four then tell BASIC what port to use. That's also going to be the console port with an 88.2 SIO. So the fact that the load port and the console port are the same, that is the signature of a teletype. In other words, it's all coming through the same serial port. So we are configured to use a teletype. So we hit run, and now this is ready to load. Let me go ahead and come over here to the rest of our Glass Teletype. So just like on a real teletype, we've now hit read on the paper tape reader, and off it goes. Now this is going to load very quickly. It takes about 4.5 minutes on a teletype, and here we'll be done in just a few seconds. Now this is quite a bit faster, the 4.5 minutes, than the 12 minutes we talked about, or 12.5 for the 4K Basic on the Southwest. Why is it so much quicker? It's because in the Altair it was loaded as a binary image, whereas on the Southwest Technical it was loaded in S-record format, which is a ASCII hex representation of the data, almost a 3-to-1 overhead for the same data. But at the speed of this high-speed reader, that's hardly even noticeable. It doesn't make much of a difference. I'm having to dodge the paper tape down here. Let me do a quick video cut and we'll continue from here. I'm going to clean up this paper tape before I step on it. All right, now it's safe to move around. Okay, so there's our memory size prompt from the boot. Hit return, let it size memory. Terminal width, use the default. Yes, we'll use the trig functions, and we have an empty computer here now, empty program memory, and we're ready to roll. So let's go ahead and write a little program. We'll do the usual, just like we did with the Southwest. I never do remember the deletes on these different things. Okay, this should be the same program I just did on that other one. Let me see if I got line 20 right. Yes, I did. So that underscore is on a teletype would be the back arrow button, and that's how deletes were done. All right, so now we're in the exact same position we were in the previous video. We want to save this for future use. How would you save it here in Altair Basic? Well, you don't have any sort of load and save programs, again, just like on the Southwest, but now there's no monitor to go to save it. How was it saved? Well, all you would do, oops, sorry about that. All you would do is type list, turn on your punch, and then hit return. This would then slowly print out on the teletype, but while it printed, it was actually making a tape of this exact same data. And this data is the exact same thing that you would type in when you were typing in the program. So we'll see that we could just read this listing back in, and it will be like we were typing it in, and that's how the read is done. All right, so let's go ahead and do this. You'll type list without hitting. Let me scoot back here so we can see the punch. You'll hit list like you're wanting to list the program. Come over here, turn the punch on, feed a little bit of leader, and hit return. Then punches it. Now you feed a little bit of trailer out so you can rip it off. And now we have the whole program saved just in straight ASCII on our paper tape. All those steps were the exact same thing you would have done on an actual teletype, no change whatsoever. Then you turn the punch off. All right, so now let's set this up to read it back in. All right, we'll come in here and I will do a new. So now it's empty. So again, now it's time to read this in. I guess I should have just stayed zoomed out so we can watch this tape. Now it's time to read it back in. There is no read command, but since this is coming through the console port, this tape will look exactly as if I'm typing this in myself as a human from a paper or a book or a listing I had. And it'll just magically be in there. So Basic just thinks we're typing it in. So I'm going to hit read, and there we go. And let's see how it works. Actually, it looks like it worked better than it usually does. But you can see it didn't work quite right. We've missed some lines and things in there. Normally I get worse results than that, so that's not too bad actually. The problem, as you might guess, is that this reader is too fast for Basic. It kept up on the Southwest Technical doing loads directly in and out of memory. It kept up here loading 4K Basic directly as binary into memory. But Basic itself is not able to keep up with the rate that this data is coming in. So how do we go about getting this to come in without errors? Well, the first question would be is how fast can Basic accept this data? Obviously on a teletype at 110 baud, it can keep up without any problems. It doesn't require any padding characters or nulls, which become throwaway characters in order to keep up. If you do a little bit of math on that, you can figure out that it's got about 300 milliseconds or so, just shy of 300 milliseconds to process a line when it comes in. And a couple of experiments will show you that Basic itself can queue up and buffer all these characters as they come in with no problem. But then as soon as the character turn at the end of a line is reached, Basic then runs off and starts processing the line. It goes through the buffered characters, parses them, converts them into tokens, moves them into program memory, updates pointers. Then when it's all done, comes back to read the next line. That amount of time needs to be 300 milliseconds or less, and then we know this will keep up. Now the way they took care of this was by adding the ability to print nulls after each carriage return line feed. And those nulls were then throwaway characters, didn't matter, they just got lost when you read it back in. Now again, with the teletype, it was slow enough you didn't need any of those. It did mention in the manual, if you're running 300 baud, you're going to have to add maybe 6, 7 nulls in there to get the right amount of time at 300 baud. So to get 300 milliseconds of delay at, well, 9600 baud, you'd have over 2 feet of tape at the end of each line with nulls. But the punch itself, the reader itself, is really only good for about 500 characters per second. So 300 milliseconds times 500 characters per second is 150 nulls I would need at the end of each line, about 15 inches of tape. And I don't really want to do that, although that would work. If I set nulls in here to be 150 and it printed 15 inches of tape at the end of each line, then this would probably read without errors. But that's just not the solution I want. What I'd rather do is take advantage of the handshaking line that this reader supports, allowing the host to throttle the reader's data coming in. And if you think about it, what you want to do is when the carriage return is received, we want to deassert RTS out to the reader. That will then stop the reader. BASIC can then go off, process the line, finish it all up. Then when it comes back and it does another input, at that point we want to turn it back on because we know BASIC is ready. It's asking for a read. And at that point, it should be able to keep up. And what's nice here is instead of having the worst case maximum read time for every line to 300 milliseconds, we're actually just using the actual time BASIC needs. It could be 100 milliseconds, it could be 50 milliseconds, it could be 290 milliseconds. Whatever it is, that's how much time it will actually take. So this will optimize the load speed. So the question is, how do you go about finding out where to patch this and how to patch it? Well, actually, it's quite simple. If you think about it, right now, while we're sitting here waiting for input, we are in the actual routine that is reading that tape in, right? So all I have to do, this is the beauty of a front panel, is come over here and hit stop. Let's see if we get this front panel in view. I'll hit stop. I'm just going to single step until I see this input light come on. It'll be just a few instructions at most. I say that, there we go. So this is reading from the status port on the 2SIO board. This is IO address 10 hex. It's reading the status register, waiting for this bit to come on, D0, to say that a character came in. So I'm going to single step this, so it's doing the in from the register. This is an E6, that's an AND immediate with a 1. It's looking for that bit to come on. It's then doing a jump of 0, meaning if it wasn't set, if nothing came in, back to this address right here. There's a lower byte, there's the higher byte, and now it's there. So this is the top of the loop. This is the input character routine. The address is 393 in hex. So what we need to do is patch 393 and have it jump to our patch. That's simple. We know where it is. So I'll jot that down, 393 in hex. So now let's take a look at what that input loop does so we get it all. I'm going to do an examine next instead of a step so we see it all. So here we're doing an in from the status register at 10 hex. Here's the AND immediate with a 1 to see if it's set. Here's the 3 bytes of the jump that we just went through, back to the top of the loop. But if there was a character, now it's here. This is doing an AND immediate, this is doing an in from the data register, which is 11 hex. So now it has the actual character typed in the accumulator. Now here's the AND immediate with 7F. This is getting rid of the parity bit, and then it's doing a return. So that's it. That's the whole routine. Very simple. We just need to duplicate that little bit of code. And if it's a carriage return, deassert RTS. And then no matter what, at the start of that, go ahead and assert RTS so that we can start sending characters again. So let's go take a look at that on the computer. All right, let's take a quick look at this patch. I've gone ahead and used an editor and an assembler to make this easy to look at here. This is simple enough. You could have done it by just hand assembling as well back in the day. All right, so here we can see that I'm putting the patch up at the top of memory. I'm assuming we've got 16K of memory just for this demo, and we're going to put it 20 hex before that. Our patch fits in that top 32 bytes of RAM, and we'll demonstrate in just a minute how you reserve that so BASIC doesn't touch it. All right, the input character routine in BASIC, as we saw, is here at 393 hex. So that's where we're going to put our hook. We're going to jump to our patch there. All right, so I've done that in an assembler by orging at that 393 and just putting a jump to our patch, which is at 20 hex bytes below the top of memory. So this right here is actually patching BASIC to jump to us, and then here's the actual patch itself up in the top of memory. So when we enter the patch, that means BASIC is going to do an input. If BASIC is doing an input, it's ready to work. So we want to assert RTS. So that's what these two instructions do. That asserts RTS out to the reader. Then we go into the loop that we saw stepping through on the front panel. We do an in from the status register. Rather than do an and immediate one, I just did a rotate right carry just to save a byte. Doesn't make much difference. And if there is no carry, we're in this loop waiting for a character to come in. When the character comes in, we input from the data register, get rid of the parity by ending with 7 F, and then we see if it's a carriage return, 0D. If it's not a carriage return, we just return with the character just like the original routine did. But if it is a carriage return, then we want to stop the reader. So these two instructions here turn off RTS out to the reader. So the reader then quickly stops. We then put a carriage return back into A because we clobbered A here and exit with the carriage return that's expected. And that's the whole patch. That's all there is to that. So how do we get this patch into the computer to actually use it? There's multiple ways. Number one, you could use the front panel and key in or toggle in all these bytes. It's about the same length as one of the bootstrap loaders to load BASIC, for example. But obviously, we went and got the MBL PROM and the ROM card, so we certainly don't want to have to toggle this in, so we might as well take advantage of the ROM card. And there's a couple of different things to do. You could actually put this code, instead of at the top of RAM here, we could actually put this code into ROM space, and then in this patch right here, jump to the ROM space instead. Which means every time you started BASIC, you would have to come here to 393 and use the front panel to toggle in these 3 bytes to make it jump up into the EEPROM. That would work just fine. Another option, to be more versatile, would be to go ahead and put an Intel hex file loader into one of your EEPROMs. Because a hex file loader could be used to load anything. It could load this patch or anything else we're working on. So it's kind of a very nice generic solution to have an Intel hex loader in EEPROM, even back in the old days. You could write your own, or other people had done it. It's not like you had to start from scratch. So that's what I've done, is I've written an Intel hex loader, and actually I already had one in existence, and I have stuck it in an EEPROM at FC100. So after I boot BASIC, I'll just jump to the hex loader, which I can then use to load this hex file, and boom, the patch is in place. All right, so let's go take a look at how that works. All right, so I've just booted 4K BASIC again. And now I can demonstrate how we're going to load the patch so that from then on we can use the high-speed reader for loading programs. So here at the memory size prompt, again we mentioned we're going to pretend we have 16K of memory, which is 16,384. I'm going to say that we have 16,350 bytes to leave roughly 32, 34 bytes up at the top of memory for our patch. And this is very common to do anytime you needed to include any sort of custom patch or driver or user routine at all. Okay, so we've got our 16K plus a few bytes up at the top to save for our patch. And now we want to load our patch. So again, we're just going to use Intel hex loader in PROM. It's on the same PROM board as our multi-bootloader PROM. I have the hex loader at FC100. Examine that and hit run. You can see it's telling us to send the hex file now. So all I have to do is hit read. Here it tells us the load is complete. And all I have to do to start BASIC up now is just hit reset, because reset is the warm start vector for BASIC. And so now we have the patch loaded and we're back in BASIC. And now we're ready to run our test. So let's go ahead and load our program that didn't load properly before, but now that we have the handshaking in there, it should. So I'll stick this in here, I think. Yeah. There we go. So now all I have to do is hit read. And you can see this time it came in through all of our lines without an error. Now that syntax error at the end happens every time you load a program, because when we punch the program, this OK gets punched to the tape every time. And that syntax error is on the word OK. But if you look, the whole program came in fine. So that handshaking worked very well. But what's really interesting is to watch it on a bigger program where you can see the pauses happening. So I'm going to stick in Lunar Lander, and we're going to go ahead and watch that load so you can get a feel for how that handshaking is going on at the end of each line. All right, so that's loaded. Let me clear out memory here just so we can prove that we're doing it. All right, so this gets a little jumpy. So I'm going to, there we go. I'm going to stick this on a screwdriver to be a spool so that it doesn't get out of hand. All right, and just watch how jumpy this is as it reads it. You can kind of see all the pauses happening. Hit read. All right, I got a pile of tape on the floor I got to watch out for. And there's the program. It all came in neat and clean, and you could see that jittering at the end of each line. But instead of waiting 300 milliseconds at the end of every line, we were waiting much shorter on a short line and longer on a long line. So we actually optimized the loading time that way. And you can, of course, run the program, and it's working. All right, and you've seen me do this program 100 times, so I'm not going to do that again to you. All right, well, that does it for this video. So I've got myself a Glass Teletype here that works quite well. The only situation we ran into where we really had to do any custom work or patching was, again, to load programs in BASIC on the Altair where we had to throttle the reader because it couldn't keep up. And that was a fun project on its own. Anyway, I don't know what the next video will be about and related to this paper tape reader and console. I've had fun doing this. We'll see how this Glass Teletype might work in some other situations, possibly in a future video.